In exercise 11, we are asked to calculate the global optimums of function f in set A such that x is greater or equal than 0 and less or equal than 5. I added a first section where you are asked to calculate the optimums not only in A but in all R2. So here you have the first derivatives. F has an only critical point, which is the point 5, 3. Here you have the Hessian matrix at any point, and here the Hessian matrix evaluated at the critical point. This matrix is negative semi-definite using the eigenvalues method. So we can know by the moment if this point is an optimum or not. So to use convexity or concavity of function to study the global optimums of this function in R2, I must study the sign of this Hessian matrix in R2. The eigenvalues are 6 times x minus 5, and the second one is minus 2, which is always negative. But the first eigenvalue changes its sign depending on the x. So the Hessian matrix HF is indefinite in R2. F is neither convex nor concave in R2. Then, in this case, we can't use the convexity or concavity of the function to know if this point is or not a global optimum. But we can know it just by having a look to the function. Have a look at this function. The function evaluated at the critical point is 15. Now, I calculate, for example, the value of the function at the point 6, 3. This result is 1 minus 0 plus 15, which is greater than 15. So I know that the critical point is not a maximum because I found another point such that its image is greater than that of the function at the critical point. Now I look for a different point where its image is less than 15. For example, I try with point 5, 4. Its image is 0 minus 1 plus 15, which is 14 less than 15. Then the critical point is not a global minimum because I found a different point the image of which is less than that of the critical point. So by this process I can conclude that 5, 3 isn't a global maximum nor a global minimum in R2, so it isn't a global optimum in R2. as there isn't any other critical point, we can conclude that there isn't any global optimum of f in R2. Now, we go to section B. We are going to study now the convexity or concavity of the function not in R2 but in set A. The first thing we must check is that A is a convex set. Here we have its graphic. This is set A. We can check that if we joined any pair of points in this set, the segment is fully contained in A, so A is convex. Moreover, A is the intersection of two semispaces. This one, which is an upper semispace, and this one, which is a lower semispace. So, it is proved that A is a convex set. Now, the Hessian matrix is the same as before. The eigenvalues, of course, are the same as before. And now we must study the sign of these eigenvalues. The difference is that now x is less or equal than 5. So, x minus 5 is less or equal than 0. Accordingly, the first eigenvalue is less or equal than 0. So if we have an eigenvalue negative and a negative eigenvalue and an eigenvalue being less or equal than 0, we can conclude that the Hessian matrix evaluated at any point in A is negative semi-definite. So, negative semi-definite in A. Don't forget to say where we are studying the function. So, function f is concave in A. Then the critical point 5, 3 is a global maximum of f in A.